Great overview of several OCSSW functions. I'm going to go into a deep dive on L2 gen, otherwise known as the Level 2 generator. So this notebook is called Orientation to Level 2 Generator. You can download it by doing right-click, save link as, just like we have been doing all week. Okay, and so it looks like this. Jeremy has also edited this notebook with me. I want to note we also have a second one on the GIOP, the Generalized Inherent Optical Property Inversion Model within the L2 Gen program. So there is a notebook on the website for you to look at. We're not going to present it, but definitely recommend you guys taking a look if you're interested in the GIOP and producing IOP outputs from OCI data. So like Karina mentioned, this notebook was designed to use cloud-enabled OCSSW programs, which is amazing that we have that. This notebook has to run with OCSSW tag V2025.2 or higher, which the tag we have in CryoCloud is 2025.2. And let's see, this is a pre-run notebook as well, so you're welcome to follow along. The code that actually runs L2 Gen does take several minutes, so that's why it's all pre-run. But the OCSSW repository, like Karina said, NASA's OBDAX operational data processing software package. The Level 2 generator, it generates Level 2 data from calibrated top of atmosphere Level 1B data. It atmospherically corrects the top of atmosphere data, so the atmospheric correction process is within L2 Gen, so you can actually see what we do and change parameters within the atmospheric correction process if you want. Okay, at the end of this notebook, you'll know how to navigate and open files within the directory, which I found really useful to be able to see all of the different defaults that are used for OCSSW programs such as L2 Gen. You'll learn how to process Level 1B to Level 2 using L2 Gen with geographical boundaries, how to extract geographic regions from a Level 2 file, and then how to make modifications to L2 Gen based on your research needs. So we'll begin by importing the packages. This is the same setup that Ian helped explain. We are declaring the OCSSW path, seeing that it exists. We're seeing which tag we have, so you can run install OCSSW -- installed tag. You can see that we're using the V2025.2. Tags beginning with V are operational tags, while T tags are equivalent to a beta release and are meant for testing. I always say, make sure you're using a V tag because T tags could have some bugs that they haven't figured out yet. And I remember V versus T, victory. V stands for victory. We finished the tag and you should use a V tag. Okay, so this is setting up our AWS credentials, same thing. And now we'll get into navigating OCSSW. So you can actually find where this is located if you go to Shared, PACE Hack Week, you'll see an OCSSW folder. And within that folder, you can see the subdirectories of the OCSSW programs for OCI and the common ones. So if you go in here, you can see, I'll expand this, all of the different files that OCSSW grabs. You can also do this by running ls OCSSW root /share/common. And these are the files that control OCSSW processing. There's a lot. You can scroll through here and see all of them. Tip, I don't know if we've said this before, but this blue bar, you can click to collapse an output. And then it takes me all the way down. But if an output is really long, like L2 Gen outputs, you can use that blue bar to collapse the output. So clearly there's an intimidatingly large number of files required to process satellite ocean color data. The most valuable are those ending in .par. These are the parameter files that Karina explained. And they typically define the inputs, outputs, and the different options. Fun fact, and I'd love to hear Brian's commentary on this, you'll see in here, let me enlarge this. So you'll see L2 bin defaults, you'll see L3 map gen defaults, you'll see some other stuff. You'll keep going and you'll say, where's L2 gen? Well, the fun fact is L2 gen used to be named multi-sensor level 1 to 2 or MSL 1.2. That is why many PAR files start with MSL 1.2. The OBDAC started to rename most programs like L2 gen or L3 map gen to more clearly identify their purpose. But the PAR files for use with L2 gen still have names that begin with MSL 1.2. So just remember, MSL 1.2 equals L2 gen. And I'd love for you to ask Brian, can we change this? Because it is a little confusing and something I just learned. So just remember, anything that starts with MSL 1.2 is essentially L2 gen. Is that right?
Yeah, not created.
Okay, so let's look at the specific PACE OCI specific files. So you can do share/OCI. Take a look at those, and then we can actually open up a file. So the cat command here, well, let's open up the MSL 1.2 default, so the L2 gen defaults parameter file. So how the OBDAC or ODPS processes data, these are the default commands to process level 2 OCI data. So they're using the OC data suite. Is that right, Brian? Sorry, okay, I heard mingling. Correct me if I'm wrong about any of this, but this is the defaults that they use to create level 2 files that we can get from the Earth Data Cloud. So these are the aerosol models they use for atmosphere correction, the wavelengths they use, different algorithm controls, the GIOP wavelength they use for optimization. So a lot of really useful information in these files that you can go look at. You can also use the help to see what inputs to be put. I'm going to collapse this. And we're going to write our own OCSSW parameter files the same way Karina introduced by using this little function called write_par. So we're going to include an I file, O file, and some other parameters. So we'll go ahead and find some level 1B data. So this is similar to the notebook I presented on Sunday. We're going to use earthaccess.search data to find some level 1B data. We're going to open it. We're also going to do the same for a corresponding level 2 file, which we'll use later. We'll open that as well. And then we'll do a quick plot to see what we're working with. So this is the big granule, level 1B granule that we're going to process. And you can see right here in the top left-hand corner is maybe a water body that looks familiar to some. It's the Chesapeake Bay. Okay, so let's run L2 gen with its default configuration. So before we do this, there's one additional step required to exactly replicate a level 2 file from OBDAC, or that you would get from NASA Earth Data Cloud. So the algorithms within L2 gen require ancillary data such as meteorological information, ozone concentration, sea surface temperatures. So we want to use the corresponding ancillary data for the given date and region. So we need to run an OCSS function called getAnts, get ancillary data. If getAnts is not used, L2 gen uses climatological data found in the shared/common directory. So we can run the help function to see what getAnts needs. So so here's the options of everything you can put in. This is just some code to declare the level 1B path and name, and then here is where we're running it. So here's getAnts. This could be confusing to some. To be honest, Ian helped me write this as well, and this is more efficient ways to run the OCSSW functions. So it's just using file name of the level 1B name that we declared up here. It's using the level 2, it's producing the O file called level 2 ants. And you'll notice after you run this, you get a file in your working directory called level2gen.ants. And reading this file, you can see that the ancillary data is saved in the var/ants directory. You can open this so you can see all of these files were grabbed from various databases and they were put in this ants folder in our shared directory. Does that make sense? So now that we have our ancillary data, we can make a par file that has an I file, an O file, latitude and longitude boundaries. We're going to be subsetting the level 1B file to a smaller region because level 2 gen does take a long time on a whole granule. It can take up to, I don't know how much on CryoCloud, but probably like 15, 20 minutes. So we're doing a small subset that will take about 3 to 4 minutes. So just, if you're doing this in real time, just know that it's going to take a little bit. So we're going to create a folder called data where we're going to store these outputs. Here is the par file that we're writing. So we're going to use these geographical boundaries. We're going to say level 2 product should be RRS, and we are not going to produce uncertainties because that takes even longer. So let's run it. So this is the command to run it. So we're saying par equals l2gen.par, and we're also using the l2gen.ants file to read in our ancillary data for l2gen. So here's the giant output that you'll get. It's really giant. You can read along as it goes. It's doing all the necessary stuff. Here's the following products. Begin processing, blah, blah, blah. Here's our ancillary data. Here's all the lookup tables it uses. Here we go, keep going. And then it does different scans. So this subset has 382 scans, so keep going. And you can see here, this is where it takes a while. So it goes through and it processes all 382 scans, and then at the very end you'll know it's done when it says processing completed. If it doesn't say processing completed, it didn't process. You probably got an error, and we would need to troubleshoot what's going on with your par file. So we can open up this new level 2 data. So we're going to open up the O file that we declared in the par file. And so we open it up with an X-ray data set. You can see all of the variables. We see RRS, yay. Let's do a quick plot of RRS at 550, and it looks like this. So this is the subset of the Chesapeake Bay that I declared when running L2Gen. Cool. Any questions so far? How am I doing on time? Yeah, 2 questions. Go ahead.
Yeah, if I don't have Amazon account, will it work?
Yes, you have to install the OCSSW directory locally, and we have a notebook on that on the Help Hub showing how to install it locally on your laptop. There's a notebook on the Help Hub. We talked about that the first day, and I can give you the website, but there's a notebook that we created to explain how to install the OCSSW files locally on your laptop.
But just to be clear, though, that you all have the AWS access with CryoCloud for this, so you don't need to pay for your own. This is what Ian talked about. If you're using it a lot, and you might want to contribute eventually to CryoCloud, but by default, it is free with your use of CryoCloud, so you don't need your own AWS account.
And I highly encourage you to use it on CryoCloud because we are maintaining the OCSSW directory, and we'll update it with the future tags. So it will be a little bit easier for you because we have done all the background effort to make sure that it works properly on CryoCloud. It can be a pain when it's on a local computer. Yeah, Eli?
So for the resolution, like in the level 3 gen, can you create your level 2 product at different resolutions?
I believe so.
Yeah. But you can choose a resolution for level 2 gen, right? Well, I use an option for resolution, but I don't know.
If you can take a look if you do L2 Gen help. I don't remember where it went.
L2 Gen, take the level 1B file, make the level 2, and take it forward, and make it solid for him.
Okay.
Okay.
But there is something called L3 Gen, which takes a level 3 product and can do much of what L2 Gen does.
Like what is it? Oh,
Well, it takes like a level 3 remote sensing reflection product to run chlorophyll or IOPs or whatever.
from a level 3 file?
Level 3 file.
Okay. Didn't know that.
But you use the term L3 Gen, that's what L3 Gen actually is. There's L3 bin, L3 map gen, and then L3 Gen. You missed all that.
But because I am certain there is an option for resolution, but maybe we don't need it. It will create the same, but we can modify it. It's there.
The level 1 data in culture resolution, and that would be
Yeah, it follows whatever the L2 Gen outputs whatever the level 1 input resolution is. I don't believe there's any. There may be something that says resolution.
I think
but
there is, but yeah, I'm not sure exactly what it does.
I'm not sure what product or what parameter it is. Jeremy's looking.
Okay.
Any other questions before I continue? Okay. Okay, so we just processed a level 2 file ourselves. Let's compare that newly generated file with the one we would find on NASA Earth Data Cloud. So we downloaded it previously. However, that level 2 file is the giant granule, so let's subset it like we did in L2 Gen, so we're comparing apples to apples. So we can do that by using some other programs, some other OCSSW programs called LonLat2PixLine. So here we're just changing some file names, and then we're calling LonLat2PixLine, and this gives you the pixel, hold on, the pixel values that you need to run L2 extract. So this is a little confusing. LonLat2PixLine, if you put in the latitude, longitude boundaries of your area, it gives you the pixel values, the scanline values, and then you can put those in to L2 extract. And that creates a new, smaller file that only includes our defined geographic boundaries. So we run that down here, and then we can open that new file, and we see a plot that looks almost exactly like the one we plotted before with our homegrown level 2 file. So the two maps look extremely similar, but let's compare the data in a scatter plot. So here I'm comparing the user produced, what we produced through L2 Gen RRS at 550 versus OBDAC RRS at 550, or what we grabbed from NASA Earth data. So other than a couple of oddball points, the data are identical. This shows that an end user can exactly reproduce the data distributed by OBDAC. Cool. Okay, let's run L2 Gen with some modifications. Yes?
Just to clear up the resolution thing, you cannot set the resolution in L2 Gen.
L2 Gen, okay.
No, there is one very specific option for MODIS. MODIS has ocean bands at 1 kilometer. It's got 2 aerosol bands at 250 meters and 2 land bands at 500 meters. You can trick L2 Gen into processing ocean color at 500 or 250 meters because those pixels exist for MODIS.
Right.
But there is you can't take OCI and do different resolutions or anything like that. Just clearing that up.
Okay, thank you. Okay, so let's say you want biogeochemical data products through L2 Gen. So there's 2 ways to do that. You can assign a specific product suite. So for chlorophyll, let's say you want chlorophyll, you can add the suite in your PAR file, suite equals BGC, biogeochemical data. Or you can exactly define your output products in a list using L2 prod, which you saw above. So let's let's say we want RRS, but also chlorophyll and also particulate organic carbon and L2 flags. You should always include L2 flags. It is always included as an output product, but this helps you identify processing flags assigned to each pixel to see if the pixel, how the quality of that pixel. Let's see, okay, so here's our par file. We're using L2 prod equals all of that. We're using the same geographical boundaries, and we're gonna run it. So we're doing, using that par file and also using the same ancillary file that we generated above. And again, you'll get a giant output, la 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 la, la la la, and processing completed. So you should now have a new level 2 file in your data folder. We can open it and plot the chlorophyll variable, and it looks something like this. So now we have ourselves ran L2Gen on a level 1B file to generate chlorophyll data. And then this is just plotting it again, but with some additional plotting functions using a pretty color map, just an example of how you can plot the data that you just processed. And then as a final example of the far-reaching utility that L2Gen can provide, let's do one more example. Let's say you want to, and this is kind of getting into the, the weeds of how we process data, but let's say you want to disable the bidirectional reflectance distribution function, or the BRDF, and let's see how that changes the retrieved RRS values. So the default is BRDF op equals 7, which is the Morel correction. But in this example, we're going to say BRDF opt equals 0. And let's see what that does. So again, we're using this new par file, the same ancillary file, and we ran it, la 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 la. And we open it. Let's plot RRS at 550. It looks similar to what we produced in section 3, but let's make a scatter plot. And you can see this is RRS at 550 using the default BRDF, and this is when it's disabled. And so you can see that there are some changes in the RRS values if you toggle these different parameters within L2Gen. So this is just an example of disabling the BRDF, but there's hundreds of different, thousands of different ways you could toggle different parameters to get different results. So I hope this is useful. I just want to show you very briefly the GIOP one. So it's similar to this, but it really does focus on, how do I make this bright? So this, yeah. It focuses on the GIOP model. So it produces IOPs, goes into what they all mean. It goes into what we're trying to get from this inversion model. We're trying to retrieve the eigenvalues of this ocean color inversion model to be able to better estimate absorption and scattering of optically active constituents. And so down here at the bottom, you'll just see that I was able to run L2Gen /GIOP to plot all the different IOP outputs. So we have, we have absorption, backscattering, phytoplankton absorption at 442. We have the slope of absorption of detritus and gelbstop. If this means nothing to you, don't worry. This is a pretty specific tutorial for those that are interested in ocean color inversion modeling. And then here I show an example of 2 pixels plotting the spectral shapes of absorption, total backscattering, and phytoplankton absorption. So, I mean, right, if you're interested in looking at phytoplankton absorption for your group, this is how you would process it and get the shape of phytoplankton absorption. And you can see that they're different because my points, one is in more coastal waters, I guess, versus open ocean waters. Okay, that's all I have. Unless I have another plot down here. What did I do down here? Oh, this is showing an example of running GIOP with different calculations of the slope of the CDOM parameter. So showing how absorption of DG, detritus, gelbstop, I don't even know how to say that word, gelbstop, CDOM, a detritus, how it can differ using different calculations for the slope. So, any questions? Oh, someone left their phone in the other room. If this is yours, I have it. Nope, there it is. There you go. Yeah, Ryan?
I'm going to put my ignorance on full display here, but is there any like fundamental difference between using like these IPAR files? It always kind of seemed a little like convoluted for me. For me to like wrap my head around it, I would just run L2Gen in sort of a single line and then wrap it in like a bash script,
Sure.
direct it towards a whole directory of files and be like, all right, go to town.
Yeah.
Is there fundamentally like something by using the PAR files that you gain, I guess, relative to doing that, or is it just kind of doing the same thing in a different way?
I think it's doing the same thing in a different way. For me, I like to see my options, and it allows me to edit things more clearly doing it this way, describing or just, making my own PAR files. But so you're saying you would do it just via command line and have it run with one single L2Gen. I just feel like it's hard to
I'm old
change
school,
things
I guess.
that way.
Yeah, I just like to see what the command line like exactly is sort of doing.
Right.
So not.
Yeah, if that works for you, I think that could be a very long.
Yeah, it is usually.
Yeah, and so this is easier for me to conceptualize all the different options that I'm changing.
Okay. Yeah, it just
But
cleans
I
it
think
up a little
it's
bit.
the same
kinda.
thing. It's
All
just
right.
user preference. Okay. And maybe I should say really quickly, I don't have it done because we needed a new tag. We actually have V2025.3. There is a way, I know some of you might be interested. You can use L2Gen/GIOP on CBAS data. So data files ending in SB, so essentially in situ RRS, if it's formatted the right way, which I have a tutorial on how to do that, you can input that into the same exact L2Gen call, and it can produce IOPs on your in situ RRS. So I think that could be very powerful to some. So look for a tutorial in the future on how to do that. So yeah, I'll try to have it up on the website maybe, I don't know, next week. It's almost there, but I needed a new tag.